by taking a look at the equipment that we have in this second segment. I've got a coil of wire, and there's many turns of wire which is wrapped around this opening here. So I have a coil of wire. Connected to it is two LEDs, and LEDs have a special property. They only light when current goes in one direction, and there's two LEDs. One of them is blue, one of them is orange. One of them lights when current goes around the coil in this direction, the other lights when current goes around the coil in the other direction. And so we'll be able to tell if there's current flowing by if a light bulb lights. And we'll be able to tell the direction of the current by the color of the light that flashes. Now I have a very strong magnet here, and if I take this very strong magnet and bring it in and put it on top of the coil, watch what happens. The blue bulb turns on, but just for a moment. But just for a moment. And here's the thing. There's a connection between magnetism and electricity. There's a big connection, as we saw in the last segment, and it looks like this. A changing magnetic field can induce an electric current. Not a magnetic field per se, but a changing magnetic field. And I have a changing magnetic field inside this coil causes the bulb to light. Right now, there's no magnetic field inside the coil. But if I bring the strong magnet in and put it on top of the coil, the blue light bulb lights. And it lights during the time when the field is changing from being 0 to being a lot, okay? So I have a changing magnetic field inside the coil. Now we're going to describe the changing field inside the coil in terms of a concept known as flux. And flux is basically a product of the magnetic field times the area of the loop. So I've got a coil that has a certain area, and the area is the cross-section area of the coil. Right now the flux through it is 0 because there's no magnetic field inside the coil. But if I bring the magnet and put it on top of the coil, all of a sudden there's a strong magnetic field inside the coil, and so I've had an increase in the flux through the coil. And that causes the light bulb to light. So now I want to do a series of experiments with the magnet and the coil. And here's what we'll do. Right now the flux inside the coil is 0. Okay? The north pole of the magnet is pointing down. So I'm going to make a flux through the loop that's downward. Okay, so let's watch the lights. When I bring the magnet in, and I'm going to have a flux going down through the loop. Here we go. And what lights? The blue bulb. So that meant the current went in a particular direction. Now I have a question for you. I'm going to take the magnet and I'm going to pull it away. So there's a huge downward flux through the coil. What happens when I take it away? Will a light bulb light? And if a light bulb does light, which bulb lights? The blue one or the orange one? We'll give you some choices. And you probably guessed what's going to happen. When the flux goes from 0 to a large downward flux, the blue light bulb lights. When the flux goes from being a large downward flux to 0, the orange light bulb will light because it's the same magnitude change, but it's in a different direction. 0 to a large downward flux is an increasing downward flux. When I go from a large downward flux to 0, it's a change in the other direction. And so when we take a look at this, when I take the magnet away, the orange bulb lights. The blue lights when I bring it in, and the orange lights when I take it away. And in fact, I can just move it back and forth like this, and I'm going to have current going in one direction and then current going in the other direction, corresponding to an increasing downward flux and a decreasing downward flux. In the book, we have two rules that describe change in flux and the resulting EMF and the resulting current. Lenz's law tells us the direction of current that will result from a change in flux. And what happens is this. There's an induced flux that opposes the change in flux. Okay? And we're going to look at some examples of that. Faraday's law talks about the EMF that produces this current, and the EMF is proportional to the rate of change of the flux. Now we can see the dependence on the rate of change of the flux this way. If I take the magnet and I move it away very slowly, the flux is changing slowly, and the light bulb doesn't light. But if I gradually increase the speed at which I do this, the light bulbs begin to light. And if I go very fast, the rate of change of flux is very high, and so the net result is I get very, very bright lights because I have a high EMF, and so I have lots of current. That's a representation of Faraday's law. When I put a flux downward through the loop generates its own flux that's upward. When I take away the downward flux to the loop, it's going to oppose that change. The loop puts in its own downward flux. And so the current will go in the other direction. When I put in the south pole, I'm making an upward flux. And when I put in a strong upward flux, the loop makes its own downward flux. But when I take the magnet away, I'm taking away an upward flux, and so the loop makes its own upward flux. It's always opposing the change in flux. And we have some graphics in the textbook that will help you make sense of this. And there's one last piece of the puzzle that we want to look at, and that's the forces. Now think about this. I have a very strong magnet. I'm going to bring it near, not a loop, but a piece of copper. And it turns out, if I take a magnet and bring it near a piece of copper, I can have currents inside the piece of copper. They're so-called eddy currents. And think about this. North pole of the magnet is down. I'm going to bring it down on top of the copper. I'm going to induce currents inside the copper. Those induced currents will make a field. I'm putting on a field that goes down, so the downward field that I'm applying is increasing. This piece of copper will have induced currents that produce their own field. What's the direction of the field due to those induced currents? We'll give you some choices. I'm putting on a strong downward field. So there's a downward flux that's being produced through the copper. So the copper wants to oppose that change, and so it generates its own upward flux. Now let's think about the forces between the two. There's a downward porting field, and so the bottom of this magnet is a north pole. The copper makes an upward field, and so magnetically the top of the copper is going to look like a north pole. And so there will be a force between the copper and the magnet. North pole on the bottom of the magnet, north pole on the top of the copper. What can you say about the force between the two? We'll give you some choices. And this is one you know. I have a north pole on the top of here, north pole on the top of here. It's a repulsive force. And so if I take this magnet and drop it on the copper, what happens is this. It falls slowly and settles down ever so gently. There's a repulsive force between them. And this is a fantastic application of Lenz's law. So we've seen there's a deep connection between electricity and magnetism, but it goes deeper than this. Changing magnetic field induces an electric field, but it works the other way as well. And that is responsible for some of the most fascinating topics in physics. We'll take a look at that in the next segment.